Hi, so I'll be talking about hardness of constant round communication complexity, and this is joint work with Shuichi Hirahara and Bruno Loff.
So the main motivating question behind our paper and this line of work is the following. How hard is it computationally to compute communication complexity? So communication complexity is this model that we all know and love. But if you look at it from a computational perspective, like what are the properties of this complexity measure? Like, is this a complexity measure that's easy to compute? Is it in polynomial time? Is it NP hard to compute? Is it hard to approximate? Those are kind of the motivating questions behind this paper. So let me begin by just recalling definitions in communication complexity. I guess probably everybody is familiar with this model, but just to make sure we're all on the same page, let me introduce it anyway. So in communication complexity, you have some function f, and this is a two-party function. It takes inputs x and y. And we're in the setting where one of our players, maybe Alice, has the input x, and another one of our players, Bob, has the input y. And their goal is to communicate with each other while using the least amount of communication possible in a way that they're both able to learn the value of the function f. So their goal is to compute this function f while minimizing the amount of communication they have to use between themselves. So to make this a little bit more formal, we say that a protocol for computing f is given by some binary tree, which has some kind of underlying functions and labels associated with it. And in this binary tree, you have nodes, and each node is either indicates a speaker, either Alice or Bob. And to follow the communication protocol, what you do is you'll trace down the binary tree. So you'll start at the root, and then based on Alice's input, she'll either say 0 or 1, and then based on that message, the next speaker will go, and let's say the next speaker is Bob. And so based on Alice's prior message and the input that Bob has, he'll either say 0 or 1, and they'll keep going on like this until they reach the leaves of the tree, and the leaves of the tree are either labeled by yes and no. And this is a protocol for f if this procedure actually correctly computes f on all different inputs. And so for us, we'll be interested in two different size measures. One is the communication complexity of a function, which is the minimum depth of any protocol for computing f. So it's the minimum depth of this tree. But we'll also be interested in maybe a more refined notion of size, which is leaf complexity. And the leaf complexity of f, of a function f, is the minimum number of leaves in any protocol for f. And it turns out that these two quantities are very closely related. The communication complexity of f and the leaf complexity of f are basically the same up to a logarithm by doing some rebalancing. But yeah, I won't get into the details of that.
So I mentioned this question earlier about computing communication complexity. So let me make that question formal. So what do I mean by computing communication complexity? We're interested in the problem where if you're given some function f, and for us, you can think of f as either a two-player function, or you can think of f as some matrix, and your goal is to compute the communication complexity of f. And the question we're interested in is, how hard is this problem? Do we expect there to be an algorithm that solves this? Do we not expect there to be an algorithm that solves this? Do we think it's easy to approximate, and so on? So that's the question. And there's one kind of major prior result along these lines, and that's by Kushilevitz and Weinreb. And Kushilevitz and Weinreb, they're kind of interested in this question from kind of a meta-complexity perspective. In particular, they were wondering, they were looking at problems like, at the time, clique versus independent set, which since then has been kind of resolved. And they were wondering, why is it so hard to prove communication complexity lower bounds? Why does it seem difficult in some cases to prove communication complexity lower bounds, while for questions like clique versus independent set? And so they thought that by studying this question of what's the degree of difficulty in computing communication complexity, they could shed light on the question of proving communication complexity lower bounds. And so their main theorem, Kushel-Levitt and Weinreb showed, was that computing communication complexity is actually hard under cryptographic assumption. So in particular, they showed that computing communication complexity up to some small constant factor is impossible under some crypto assumptions, in particular pseudorandom functions and NC1, and this is like a relatively reasonable cryptography assumption, at least in my opinion. And they also show something else, which is that under a conjecture, no polynomial time algorithm can compute communication complexity even up to a polynomial. So they kind of show unconditionally that strong cryptography implies hardness of communication complexity up to a small constant factor. And here, under some communication complexity conjecture, that seems maybe plausible, but also I'm not sure. I'm not an expert on it, so not totally sure how to evaluate it. But under that conjecture, they can show that in fact you can even get that there's no polynomial time algorithm that computes communication complexity up to some polynomial. And I'll come back to this a little bit later when we talk about the log rank conjecture, because it'll be relevant then. But in light of these two results, it's kind of two very natural, or a few really natural questions you could ask. Well, one is, well, they show this hardness result under cryptographic assumption. What about an NP hardness result? Like, do we really need a cryptographic assumption here, or what? Do we really expect that this problem should be related to cryptography, or is it really just that maybe it's easier to show things under cryptographic assumption? So that's one question. Another question is about this hardness of approximation, which is, can we make this hardness of approximation maybe a little bit more believable? Like, can we remove this conjecture here and just show hardness of approximation based on a believable crypto assumption, or maybe even better, NP hardness assumption? And finally, what about algorithms? So the Kushel-Levitt and Weinreb showed that there's no polynomial time algorithm under crypto assumption. What about like non-trivial algorithms? Can you like do better than brute force for this problem? As far as we know, as far as I know, there's no algorithm that does this. Okay, so that's Kushel-Levitt and Weinreb. And I mentioned a little bit about how this is somewhat related to the log rank conjecture, so let me just state that. So in the log rank conjecture, the goal is to estimate the communication complexity of a matrix. And so way back in, I guess, the early 80s, people realized that there's a very simple lower bound for communication complexity, which is just the log of a rank of a matrix. So if you look at a communication matrix, you take its rank and then take the log of it, that's a very simple lower bound on the communication complexity. On the other hand, Lovász and Sachs conjectured in '88 that this lower bound is actually kind of tight, in the sense that the log of a rank of a matrix, at least up to a polynomial, actually characterizes communication complexity. And so this is the log rank conjecture. It's perhaps like the most outstanding question in communication complexity right now. It's certainly the longest standing open question. And so what do we know about the log rank conjecture? So, and I should say, the log rank conjecture says that this inequality holds for some C. Okay, so what do we know about the log rank conjecture? So there is some upper bound here. We're not able to get polylog rank of M. We can actually do, but Shahar-Levitt showed that you can actually get an upper bound here that is exponential, sort of, in the rank, and that's the best upper bound we know. We also know very recently that like some generalization of the log rank conjecture is false. The log approximate rank conjecture is false. So, maybe that suggests that maybe the log rank conjecture itself is false. I don't know. And there are also some special cases of log rank conjecture that we know. So there's, this has been an area of active research, but the question of whether the log rank conjecture is true still remains kind of wide open. And the relevance of this to this line of work is the following. if the log rank conjecture is true, then that actually gives you a polynomial time approximation algorithm for communication complexity. In particular, to estimate communication complexity, you could just look at the matrix, take its rank, take the log of rank, and boom, there you get an approximation algorithm for communication complexity. And that raises the question. In fact, it raises two questions. One is, if the log rank conjecture is true, do we think that that approximation actually is optimal for the log rank? And the second thing is, should we even expect you to be able to give such a good approximation? Like, do we expect that computing communication complexity up to a polynomial is something that's actually possible in polynomial time? Like maybe this would contradict ETH, or maybe you could show some hardness of approximation for communication complexity that would rule this out. So these are two kind of interesting questions. Like, is this level of approximation even possible? Would it be optimal if it is possible? And in fact, that conjecture that second theorem I mentioned on the previous slide by Kushilevitz and Weinrib kind of answers yes to this in some way. That if that conjecture is true, then actually log rank is optimal in some sense. Okay. So that brings us to our results. And so let me begin by stating our main theorem kind of informally, and then I'll come back and define some terms. So our main theorem informally is, at least if you limit yourself to the constant round setting, then computing communication complexity is actually NP-hard. So whenever r is greater than or equal to 3, computing r round communication complexity is NP-hard. And so you might be wondering, like, okay, why is it 3 here, not 2? Well, it turns out that 2 is like a very simple thing. Actually, I'll tell you how to compute 2, but it turns out to be very simple. Okay, so that's the theorem. So let me start by defining constant round communication complexity. So for us, an R round protocol is defined by a depth R tree, which is rooted. And now, in contrast to the prior case, nodes can actually have multiple children. So in our prior protocol, we were assuming that the nodes had like binary children. In this case, we'll allow you to have many children. And then it works pretty much the same as before. So then maybe the first node, maybe Alice speaks there, and now Alice is able to say 0, 1, 2, or 3. And then based on that, then like the next person speaks, and maybe that's going to be Bob, and he can say based on what he received from Alice and what input he has, either 0, 1, 2, 3, or 4, and so on. And for us, kind of the relevant size measure is going to be the leaf complexity when we restrict to one player going first. So L Alice R of F is going to be the minimum number of leaves in any Alice first R round protocol for F. Yeah, so two comments I want to make here is that actually our choice of leaves here is important. It turns out when you look at constant round protocols, kind of leaf complexity makes a lot more sense than bit complexity. So there, in that sense, it's important that we make use of leaves here. And the other thing is that we're actually restricting the case where Alice speaks first or Bob speaks first. It turns out that like you can actually get rid of this restriction with some cost, but I'm going to talk about it in this way because it makes our theorems kind of nicer to state and so on. Okay. And so one final thing I want to note is that even the constant round setting is kind of interesting in the sense that if you could characterize the hardness of approximation of the constant round setting, it actually still could, potentially refute the log rank conjecture, because the log rank conjecture actually implies some sort of approximation for the constant round setting too. Yeah, I don't want to get into this too much, but basically the idea is any protocol with an unbounded number of rounds can actually be turned into a protocol with a bounded number of rounds with some sub-exponential size blowup. And because of that, you can actually show that the log rank conjecture would imply some sort of like very weak approximation for even the constant round setting. And this weak approximation, it's not clear whether it should be hard or easy for this problem. Okay. So now let me state the main theorem a little bit more formally. So the main theorem is that for any r greater than or equal to 3, computing the minimum number of leaves in an r-round protocol is NP-hard. And so this, to be clear here, we actually show some hardness approximation here, but not too much hardness approximation, just up to some small constant factor. Here, epsilon is some constant that depends on r, so you should think of this as like maybe like 1.001, and that 001 gets smaller as the number of rounds get larger. And the other thing is the NP hardness here is under polynomial time non-adaptive reductions, so relatively standard. Okay, so now let me tell you a little bit about the techniques used here. So I think the overall approach is pretty natural, so it works by induction. So the base case is 3-round protocols. Maybe there's something weird here in that, like, why do we start with 3 instead of 2? But yeah, I'll tell you why in a second. And then after we have the base case, we work inductively. So what we want to do is we want to show if the r round case is NP hard, then that actually implies the r plus 1 round case is NP hard. And this approach, and in fact the high-level approach of our results, actually follows one of this paper I wrote last year, which is about the hardness of minimizing constant depth formulas, and which also takes this approach where you start with the base case of hardness in a bounded number of rounds, or in this case bounded number of depth, and then you work up from there. And the high-level approach is pretty similar, but it turns out when you look at the details, things actually end up looking very different. Anyway, if you're interested, you can check out this paper. Okay, so now let me tell you a little bit more about how establishing the base case. So base case, maybe the first thing that you'd want to do is look at the 2-round setting. And it turns out that the 2-round setting is actually very easy. It turns out that if you have some communication matrix M, the 2-round complexity of M is actually just like the number of distinct rows in M. And so kind of the idea behind this is that suppose Alice, you're in a 2-round setting, so Alice only gets to communicate once, Bob only gets to communicate once. If Alice didn't separate to provide enough information to distinguish between, let's say, the first row here and the second row here, then Bob would have to know, based on his input and the information he gets from Alice, whether the output is 0 or 1, because this is only 2-round protocol, so Bob needs to know the answer based just on Alice's message. But if these 2 rows were not separated, and Bob had this column as his input, he wouldn't know how to distinguish the 0 case from the 1 case. And it turns out that this argument can be made like fully general, and that this like completely characterizes the 2-round case up to some factor of 2, but I'll ignore that for now. And that leads us to the 3-round case. So in the 3-round case, we also get like a fairly simple, maybe a little bit more complicated, but not too complicated combinatorial characterization. So the characterization is as follows. If you have some matrix M, the 3-round communication complexity of M is determined by the minimum number of distinct rows in M when you're allowed to restrict by any column partition. So now instead of counting the number of distinct rows in M by itself, you're actually able to split M into a bunch of different submatrices induced by some partition of the columns, and then just count the number of distinct rows on those submatrices and add them all together. So for example, here you could split this matrix into this submatrix and this submatrix, and in this submatrix you only have 2 distinct rows, and in this submatrix you only have 2 distinct rows. So then your total number of distinct rows across the column partition would be 4. Okay. And again, I'm lying here a little bit, but let's not worry about that. Okay, so now we have this combinatorial quantity, which at least seems easy to describe. it turns out that it's not too hard to show that this problem is actually NP-hard. So for our base case, we're able to show that this problem is NP-hard to approximate even to a large factor. So like if n is the size of the input matrix, then you can approximate this even to a factor of n to the 1/5. And just some notes about this. I don't want to go too far into it. It's like it's a reduction from chromatic number. The reduction, is kind of cool in that the sense that it actually does use some like de-randomization tools in there. It uses this construction of universal sets, which is kind of fun. And I want to note, even in this base case setting, there's kind of some interesting open questions. One is, can you get better hardness here? So our results, shows a hardness to a factor of n to the 1/5, and like the best you could hope for, it looks like using our techniques is maybe n to the 1/2, maybe. But, is this problem hard to approximate to n to the 1 minus epsilon? I think that's kind of an interesting question. Like, can you replace the 1/5 here with 1 minus epsilon? Or on the other hand, like, could you come up with an algorithm for computing this quantity? It seems like a relatively simple quantity, so I feel like there should be some non-trivial algorithm. The best algorithm that like we were able to come up with gave like a really bad approximation factor. I think it was like n over log n. It was kind of similar to clique. So yeah, I think even in this restricted case of 3 rounds, there are kind of some interesting questions. But anyway, that's the base case. And that leads us to hardness for more rounds. So remember, our goal here is to be able to reduce computing communication complexity in the R round setting to reduce to the communication complexity in the R+1 round setting. And so a natural approach to doing this is the following. Given some function f that we want to know the R round communication complexity of, let's construct some new function g that is related to f, such that the R+1 round complexity of g is somehow related to the R round complexity of f. And in that way, maybe we're able to compute this quantity using R+1 round communication complexity. So I think that's a natural approach, and if you were able to do this in a nice enough way, it would actually give some reduction from R rounds to R+1 rounds. And so it turns out there's kind of like a very classical tool that is able to do this. It's called the round elimination lemma. And so this was proved way back in '98 by Milterson, Nissan, Safra, and Vigdresen, and then later improved by Sen and Venkatesh. And it works as follows. It's a very nice construction. Given some function f, now you want to create some new function g. Here's how you can do it. Your new function g is going to be kind of like a direct sum of f. So you'll kind of take like k different copies of f and work with them. So how exactly it'll work is as follows. You have some parameter k, and while f took this input x and y, now what's going to happen is Alice is not just going to get x, but she's going to actually give k different inputs, x1 up to xk. And the point is that Bob will know like which input she's supposed to be, end up computing with. In particular, the output of this function is supposed to be f on the input xi comma y. But the point is that Alice won't know what I is. And if Alice speaks first, kind of like the first round is wasted. And so you'd expect that somehow the R round communication of complexity of f is very closely related to the R+1 round communication complexity of g, at least when k is large. And that's precisely what the round elimination lemma says. It says that if you look at the R+1 round communication complexity of g, it's very closely related to the R round communication complexity of f. In particular, it's upper bounded by the R round communication complexity of f up to some factor of k, and it's lower bounded by the R round communication complexity of f, except it is not deterministic communication complexity anymore. Now this is randomized communication complexity. And in particular, this epsilon here, which is determining the amount of error you're allowed in your randomized communication complexity, in order to make that epsilon small, k needs to be very large. And that's a problem because if g is going to take multiple k different inputs x, the size of this function g is going to blow up very rapidly if you let k get large. And it's going to blow kind of exponentially in k. And so this kind of introduces two problems for our purpose. One, it requires a lower bound on randomized communication complexity. I mean, ideally what we want is we want to reduce R round deterministic communication complexity to R plus 1 round deterministic communication complexity. And so if we're going to use this classical round elimination lemma, we have this problem where actually we're only able to lift a randomized communication complexity. So that's a problem. The other problem is blows up the size of the matrix kind of dramatically in order to get like the parameter is good here. Like you might need what might end up to be like a sub-exponential size reduction here, or sub-exponential time reduction here. So that's not great. So what would be great is that if you can come up with some round elimination lemma that is one, works purely with deterministic communication complexity, and two, doesn't blow up the size of the matrix. And in fact, that's what we're going to do. So come up with a deterministic version of the round elimination lemma. And it works as follows. Given some function f, our new function g is going to be kind of like a mix between the original function f and a quality. And so how it'll work is as follows. There'll be this bit I that Bob will get. And if I is equal to 1, then you'll compute f. And if I is equal to 0, then you'll compute equality. And you'll actually compute f and equality on different inputs. So Alice will get an input A to equality and input X to F. Bob will get an input B to equality and input Y to F. And if I equals 1, then their goal is to compute F. If I equals 0, their goal is to compute equality. And again, it's important here that Bob is the one who gets the value I, and Alice starts speaking. And so what we're able to prove, our kind of main lemma, is that if you look at the R plus 1 round communication complexity of G, I should mention this parameter K here is important. So this parameter, so G has some parameter K associated with it, and K is going to determine the size of this equality. So how many bits is equality going to be on? So K, that's where K factors in there. So the complexity of G is upper bounded. This is kind of like a very naive upper bound where you either compute F or you either compute equality. So you can get this upper bound here by basically skipping the first round and Bob revealing I on the second round, and then either going into the protocol for F or going into protocol for equality. So that's the upper bound. But the lower bound is kind of the interesting part. It says that the complexity of this is at least the minimum of 4K and this other quantity, which is related to the R round communication complexity of F. So it's R round communication complexity of F plus 2K minus 2. And kind of the upshot is that when K is large, this quantity becomes much bigger than this quantity, and you'll actually get that the R plus 1 round communication complexity of G is equal to this quantity plus or minus 2, which is great for us because that will enable us with a few more tricks to actually get the reduction between the R round and the R plus 1 round case. And so I don't have too much time to talk about how this is proved, although the proof, I think the proof is kind of nice, and if you have time, yeah, please look at the paper. But I can tell you a little bit more about what's going on here, and the first thing I should probably tell you is actually I've lied to you, and that you don't want to use equality here. In fact, we actually want to use some other function that's related to equality that we call XOR equality. I don't want to get into it too much, but essentially the reason why is that XOR equality has a better fooling set than equality. In particular, kind of the main ideas behind proving this are the following. The idea is to do the main idea is this thing I like to call double or something, which is that either something we want happens, which is like this lower bound, or you have to pay double for something. So in particular, either the way the proof works is it's either we get this lower bound here, or the protocol has to pay twice for equality, which is why you're getting like a 4K here. the analysis will split on Alice's first round. So basically, based on what Alice does in the first round, we'll either end up in this case or that case. And final thing I kind of want to say is that really the main idea behind this proof, or the main property we need of the equality function, is related to fooling sets, and that's actually why we don't want to quite use the equality function. We want to use something which has like an even better fooling set than equality. Okay. So that brings me to kind of like interesting open questions. I guess, this is a recorded talk, so you won't get to ask me about them, but I think some interesting questions are better hardness approximation. You should be able to get like n to the 1 minus epsilon factor hardness of approximation in the constant round case. Another thing that I think is interesting is like algorithms for communication complexity. I think there should be some non-trivial algorithms for it. Finally, there's this original question we started with, which is unbounded round communication complexity NP hard? And then there's also the question of like, let's forget about, what about randomized communication complexity? We just talked about deterministic communication complexity. What about the randomized case? All right, so that concludes my talk, and if you're interested, feel free to send me or any of my co-authors an email, and we'd be happy to talk.